This is section 2.4, zeros of polynomial functions. Real zeros. Recall that a polynomial function of degree n can have at most n real zeros. These real zeros are either rational or irrational. Let's take a look at the first function, f of x. Let's say f of x was made up of the factors x minus 3, x plus 2, and x minus 4. Notice that if you take negative 3 times 2, that's negative 6. And then negative 6 times negative 4, that's a positive 24. And if we were to multiply these three binomials out completely, the last number would be positive 24. And that's the result of multiplying negative 3 times 2 times negative 4. Let's look at the next function, f of x equals these binomials, these factors. Notice that we still have negative 3 times 2, and then that times negative 4, and that still results in positive 24. But notice that if we take 2 times 1, we get 2. The last number in the polynomial is a result of multiplying the second numbers, and the first number in the polynomial is a result of multiplying the first numbers in each factor. Rational zero theorem. If f is a polynomial function of the following form, with degree n greater than or equal to 1, integer coefficients, and the leading term, or excuse me, not the leading term, but rather the last term is not 0, then every rational zero of f has the form p over q, where p and q have no common factors other than plus or minus 1. P is an integer factor of the constant term a sub 0, so they're saying p is all of the factors of a sub 0. So in other words, if this was 24, now there's a lot of factors of 24, p could be 1, 2, 3, 4, plus or minus 6, plus or minus 8, because 8 times 3 is 24, plus or minus 12, because 12 times 2 is 24, and then plus or minus 24. P is the factors of the last term. Q is an integer factor of the leading coefficient a sub n. So if the leading coefficient is up here at 2, then the factors are plus or minus 1, and then plus or minus 2. Corollary. If the leading coefficient a sub 1 is 1, then any rational zero of f are integer factors of the constant term a sub 0. Now the way that we list all of the possible rational zeros is we do the p over q, where we list 1 over 1, 2 over 1 over here, 3 over 1, 4 over 1, and so on. And then we go through all those numbers over 1, and then we go through all these numbers over 2. So 1/2 could be a factor, or a 0. 3 over 2, 3/2 could be a 0. 4 over 2 could be a 0, but of course 4 over 2 is 2, and we would have already listed 2 over 1, which is also 2. List all possible rational zeros of the function, then determine which, if any, are zeros. So let's get the p's. The p's are the factors of the last term, right there, 4. So plus or minus 1, plus or minus 2, plus or minus 4, those are the p's. The q's are the factors of the leading coefficient, which just happens to be 1. So our p over q is just this list right here. 1 over 1, 2 over 1, 4 over 1, and so on. And then determine which, if any, are zeros. Well, let's start with the very first possible zero we could have, and that is 1. And we'll plug this in synthetically. 1, negative 3, negative 2, and 4. Let's bring down the 1, multiply by 1, that's negative 2. We have negative 2, that's negative 4, negative 4, and that is 0. Now what we have, and we find out that 1 is one of the zeros. So our first answer is 1 is the 0, is a 0. And then what we have left is x squared minus 2x minus 4. This does not factor. There are no factors of negative 4 that add up to negative 2. So there should be 3 zeros, and the other 2 zeros are either irrational or they are imaginary. List all possible rational zeros of the function, then determine which, if any, are zeros. Well, our p's over here are plus or minus 1, and our q's are plus or minus 1. So the possible rational, what did they say, possible rational zeros, I've seen it p, possible rational roots are just plus or minus 1. That's really the only possibilities we have. So let's test the value 1. We have 1, 0, negative 2, negative 1. Bring down the 1 times 1, add, that's 1. 1 is negative 1, negative 1 is negative 2. Well, 1 is not a 0 because the remainder is not 0, the remainder is negative 2. Let's try negative 1, 1, 0, negative 2, negative 1. We'll bring down the 1. 1, negative 1, negative 1, that's 1, that's negative 1. And then 1, and that is 0 right there. And there are no factors of negative 1 that add up to negative 1. What we have left is x squared minus x minus 1. That doesn't factor, so the only rational 0 is negative 1. Let's look at h of x. The p's are plus or minus 1, 2, 3, and of course I'm doing factors of 30, not 4. How about 5? 5 times 6 is 30. Now I can just kind of match it up with the other factor, 3 and 10, and then we have 2 and 15, and then 1 and 30. And there certainly are a lot of possibilities. Well, let's just start from the beginning and work our way across. Let's try 1. We'll plug that in to the box, and then we list the coefficients. 1, 3, negative 7, 9, and negative 30. We have 4, 3, 2, 1, 0. We don't need any zeros in here. Bring down the 1, that's 4, that's negative 3, that's 6, 6, and negative 24. That's not 0. So I tried 1, maybe I could try negative 1 next, and then try 2, and then negative 2, and so on. And I'll just kind of skip ahead, and the first one that we would discover as a 0 is 2. We have 1, 3, negative 7, 9, negative 30. Let's bring down the 1. That's 2, 5. That's 10. That's 3. 6. That's 15. And then we have 30. And that is 0. Now notice what we have left. We have x to the third plus 5x squared plus 3x plus 15. Now what we could do is we could try more numbers into this polynomial. And the numbers that we would look for are factors of 15. And I'm telling you now that the next number that would work is negative 5. So we could do negative 5. And we have 1, 5, 3, 15. Bring down the 1. That's negative 5. That's 0. That's 0. That's 3. Negative 15. And then that's 0. Now that would be the next 0. But that's like hunting for the rational zeros, and we would rather not hunt for them if we had our choice. And in this particular case, right here, if the ratio of the first two, 1 and 5, is the same as the ratio of the second two, if you divide these by 3, that'd be 1 and that'd be 5. If that happens, if the ratios are exactly the same, then you can factor this by grouping. So we could group the first two together and the last two together. We can take an x squared out of the first one and get x plus 5, and take a 3 out of the next two and get x plus 5. And what you have left is x squared plus 3 times x plus 5. So the other rational 0 is negative 5. I mean, we did the exact same thing, because over here what we have left is x squared plus 0x plus 3. See, we have x squared plus 3. So noticing that you can factor by grouping when it's an x to the third saves you the hassle of trying to hunt for another rational number. But either way, we end up with an answer of 5 as the other rational 0. Now, if we set what's left equal to 0, we notice that we get an imaginary. So that is not a rational 0. The two rational zeros for this one are 2 and negative 5. So 2 and negative 5 are the rational zeros. List all possible rational zeros of the function, then determine which, if any, are zeros. In this case, we have the p's as 1, 3, 5, and 15. Now we have q's that are not only 1, as we have had before, but now we have the possibility, or one of the q's is now 2. Now if we're going to list all of the possible rational zeros, it's 1 over 1, 3 over 1, 5 over 1, and 15 over 1. But now we have 1 over 2, 3 over 2, and so on. So now some possibilities are a half, 3 halves, 5 halves, and 15 halves. Well, I could try 1, and then negative 1, and then 3, and then negative 3, and find out which is the first one that gives us a 0 as the remainder. But the first one that we would run into that works for the sake of time here would be negative 3. So 1 would not work, negative 1 would not work, 3 would not work, negative 3 does. Let's list the coefficients. Negative 28 and 15. We got 3, 2, 1, 0, so we don't need any zeros. That's not going to mess us up by not having zeros. We got 2, negative 6, that's negative 11. That is 33, which is positive 5. Then we have negative 15 and 0. Now, to get the rest of the rational zeros, I have a quadratic. And we have lots of ways to solve quadratics, and it certainly does not have to, we don't have to use synthetic division to find the rest. So let's see if this factors. I'm pretty sure it does, because I see that 5 and 2, that's 10. And actually, I need a minus here, don't I? Minus 5 and minus 1, that'll be negative 10 and negative 1. And there it is factored. And it looks like if we add 1 and divide by 2, another rational zero is 1/2. And 5 makes this one 0. And then, of course, we have x equals negative 3. And there's the 3 rational zeros for this function. Upper and lower bound test. Let f be a polynomial function of degree n greater than or equal to 1. Real coefficients and a positive leading coefficient. Suppose f of x is divided by x minus c using synthetic division. If c is less than or equal to 0 and every number in the last line of division is alternately non-negative and non-positive, then c is a lower bound for the real zeros of f. If c is greater than or equal to 0 and every number in the last line of the division is non-negative, then c is an upper bound for the real zeros of f. So what does that mean? It means if your c is less than or equal to 0, in other words, negative, and when you do synthetic division, it alternates plus, minus, plus, minus, plus, minus, then you have what's called a lower bound, which means you will not have a 0 lower than that number. In other words, you can stop looking. You're not going to find anything lower than that negative number. Now, if c is greater than or equal to 0, in other words, positive, and in the last line of the division is non-negative, in other words, non-negative meaning positive or 0, so you could have plus, plus, plus. If they keep just being positive numbers, then what you found is an upper bound, and there are no zeros bigger than that number. Show f of x equals x to the 4th and blah, 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 does not have any zeros outside of negative 3 and 7. So in other words, no zeros lower than negative 3, and there are no zeros bigger than 7. If we plug negative 3 in, here's what we get. Let's see, we got coefficients 1, negative 4, negative 11, negative 4, and negative 12. 1, let's see, negative 3 is negative 7. We have 21, and that's 10. Negative 30, and that's negative 34. And then we have 102, I think, right? 3 times 4, 12, 9, carry the 1. Got it. And then this is going to be, let's see, 80, no, 90. 90? Yeah, 90, because that'll be 10. Got it. All right, so there's the remainder. Now notice that negative 3 is certainly negative, and the signs go positive, negative, positive, negative, positive, which now means there are no zeros lower than negative 3. Now let's plug 7 in. 1, negative 4, negative 11, negative 4, negative 12. Now, all of these should be positive. Let's bring down the 1, that's 7, that's 3, that's 21, that's 10, that's 70, that's 66. Oh boy, how about 66 times 7? 42, 4, 46, that's 462, and that's certainly going to be positive, 450. Now notice all of these are positive, and when that happens, there's not a 0 does not exist that is bigger than 7. That's called an upper bound. So this is an upper bound, this is a lower bound. Descartes' rule of signs. If the polynomial is a polynomial function with real coefficients, then the number of positive real zeros of f is equal to the number of variations in sign of f of x, or less than that number by some even number. The number of negative real zeros of f is the same as the number of variations in the sign of f of negative x, or less than that number by some even number. So in other words, let's look at this. The number of positive real zeros if f is equal to the number of variations in sign of f of x. So let's say there are 6 variations in signs. In other words, it goes positive, negative, positive, negative, positive for the coefficients, and it turns out there's 6 sign changes. Then there's possibly 6 positive real zeros. Then there could be 4, 2, or 0. You take the number of sign changes and then you drop that down by 2 until you would hit 0 or a negative value. You can't have negative 5 positive real zeros. With negative, you have to plug in negative x and then count the sign changes. So let's describe the possible real zeros of this function right here as, in terms of being positive or negative. F of x is, let's see, we have a positive and then a negative, so that's one sign change. Then it goes from negative to negative, that's not a sign change. Then negative to positive, there's 2 sign changes. And then positive to positive, that's not a sign change. So the number of positive zeros could be, we could have 2 positive zeros, or we could have none, because then you reduce that by 2. Let's find out what f of negative x would be. If you plug negative x into x to the 4th, it's still x to the 4th. But then x to the 3rd, that'll be, that'll still be negative when you plug a negative x in. So that'll be a positive 3x to the 3rd. And then if you square a negative, that stays the same. And then that's a 2x. That has an odd power, so that'll change signs. So it'll be minus 2x, and then we have plus 7. So we plugged in the negative x, and now we decide how many sign changes there are. And we're going from positive to positive, that's none, positive to positive. Positive to negative, there's 1 sign change, no sign change. And here's the second sign change. So the number of negative is 2 or 0. Describe the possible real zeros of g of x. 1 sign change, 2 sign changes, 3 sign changes. So the number of positive, 3 or 1. And then if we reduce 1 by 2, we get negative 1, and that can't be. G of negative x is positive x to the 3rd, because if you plug negative x into x to the 3rd, that's negative x to the 3rd, and there's already a negative out in front. Then we have plus 8x squared plus 7x plus 9. So we have no sign changes. Everybody's positive. So the number of negative real zeros, 0. There are none. Don't even check negative numbers. That's not even a possibility. The fundamental theorem of algebra. A polynomial function of degree n, where n is greater than 0, has at least 1 0, real or imaginary, in the complex number system. A polynomial function of degree n has exactly n zeros, including repeated zeros, in the complex number system. Linear factorization theorem. If f of x is a polynomial function of degree n greater than 0, then f has exactly n linear factors, and f of x equals those factors multiplied out, where a sub n is some non-zero real number and c1, c2, cn are the complex zeros, including repeated zeros of f. Write a polynomial function of least degree with real coefficients in standard form that has negative 1, 2, and 2 minus I as zeros. So the polynomial f of x is equal to x plus 1 for negative 1, x minus 2 for 2, x minus 2 minus I for 2 minus I, and then if 2 minus I is a 0 of the function, then 2 plus I must be a 0 of the function. Well, now to get the polynomial, we're going to multiply the first two together. That's x squared minus x, and then minus 2. And then for the next two, we're going to manipulate it a little bit to make it a little easier. We're going to distribute the negative through, so that's negative 2 and plus I. And then we will group the x minus 2, and the plus I will be out here. Then we'll do the same thing here. We'll make it negative 2 and negative I, and then group x minus 2 minus I. And what we've created here is the difference of two squares. Here's the difference of two squares. So when you multiply these two together, it's x minus 2 squared. And then we have x minus 2 times negative I and x minus 2 times positive I. That'll cancel each other out. And then we have I times negative I, which is minus I squared. And of course, we're going to bring the other stuff down with it. X squared minus x minus 2. And now we have to multiply this out right here. F of x equals x squared minus x minus 2, but then times x squared minus 4x plus 4. That's that foiled or multiplied out. Don't forget the negative 4x in the middle. And let's look at I squared. If I is the square root of negative 1, then I squared is equal to this squared. And the square root and the square go away, so I squared is negative 1. Well, we have a negative 1. That's plus 1. So f of x is equal to x squared minus x minus 2 times x squared minus 4x plus 5. 4 plus 1 being 5. Now let's distribute the x squared through, the negative x through, and the negative 2 through. We get x to the 4th minus 4x to the 3rd plus 5x squared. And then we have negative x to the 3rd plus 4x squared, and then minus 5x. And then we have negative 2x squared plus 8x minus 10. Now we collect like terms and we have our answer. Minus 5x to the 3rd. 9 minus 2 is 7 plus 3x minus 10. Find all complex zeros of the following. Given that 2 plus 5i is a 0 of p, then write the linear factorization of p of x. So we have to, what do? Find the complex zeros and then write the linear factorization. All right, we can do that. They tell us one of the answers is 2 plus 5i. We have 1, negative 6, 35, negative 50, and negative 58. Let's bring down the 1. We have 2 plus 5i. We're going to add, so that's negative 4 plus 5i. And we have to multiply these two together, which is 2 plus 5i times negative 4 plus 5i. That's negative 8. Let's see, we got plus 10i, we got minus 20i, and then plus 25i squared. We got negative 8, minus 10i, and then minus 25. Because remember, I squared is negative 1. So negative 30, negative 33, and that's an I there, minus 10i. So we multiply, we get negative 33 minus 10i, and we have to add those together. So we get 2 minus 10i. All right, now we have to take 2 plus 5i times 2 minus 10i. And we get 4 minus 20i plus 10i, and then minus 50i squared. And of course, we're foiling this. We have 4 minus 10i, and then plus 50. We have 54 minus 10i. So 54 minus 10i, and then we add, and that gives us 4 minus 10i. Well, now we have to take 2 plus 5i, 2 plus 5i, and times 4 minus 10i. And that better be positive 58. Let's see if that's what actually happens here. We have 2 times 4, that's 8, minus 20i plus 20i, and then 5 times negative 10 is minus 50, I squared. So these two cancel each other out. 8 plus 50, because remember I squared is negative 1, is 58. So we actually do get 58 here on the end, 58. And then that remainder is 0, and we knew that was going to happen because 2 plus 5i is a 0 of the function. Well, now if 2 plus 5i is a 0, then 2 minus 5i must also be a 0. They're called conjugates. And we're going to take what's left. We have 1. We have minus 4 plus 5i. We have 2 minus 10i. And 4 minus 10i. And we will use those now as the coefficients. We'll bring down the 1. 2 minus 5i times 1 is 2 minus 5i. Negative 4 plus 2 is negative 2. And the 5i's, they cancel out. Then we're going to take negative 2, and we have to distribute that through 2 minus 5i, which we get negative 4, and we get positive 10i, which gives us negative 2. Now, if we distribute negative 2 through the 2 minus 5i, we get negative 4 plus 10i, and that's a 0, and we knew that would happen because they're conjugates. 1 was a 0, so the conjugate is going to be a 0 also. And now we take what's left. We have x squared minus 2x minus 2. And I don't think there are any factors of negative 2 that add to negative 2. So now, unfortunately, we need to use the quadratic formula, which is a little bit lengthy, but not too bad. We have 2 plus or minus the square root of b squared minus 4 times a times c all over 2 times a. X is equal to 2 plus or minus. We have 4 plus 8, that's 12 over 2, which is 2 plus or minus 2 square root of 3 over 2, and I can divide everybody by 2. So the other two zeros are 1 plus or minus square root of 3. I have, what else did we have? We had 2 minus 5i, actually 2 plus or minus 5i. Though that's 4 zeros right there, and it is an x to the 4th, so that's all the zeros. But then it says, then write the linear factorization of p of x. So in other words, write this with factors. So the linear factorization of what? Of p of x. So p of x is equal to x minus 1 plus or minus square root of 3, and x minus 2 plus or minus 5i. And those are the factors.